after a long time.
Just we
How?
start within 1 minute. Huh?
No
Participant
problem.
are
No problem.
just
Yeah. Yeah. No problem. That's okay. Good to see you after a long time.
yeah. So how work is going on? Well,
The work is good. 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 So you are in Gujarat, right?
yeah, yeah.
Hmm. So you keep meeting Joshi sir or
Yeah. Not frequently, but
yeah, he's in now
quite
Madhya
sometime quarterly we
in there,
meet there.
right. He's Indore also, right? If he's in Mumbai, probably it is easier to meet.
Yeah.
Good, good, very good.
Okay,
Yeah,
so
yeah, yeah, no problem. Thank you.
okay, thank you. I think sufficient. Some people still not join, so they will join
Yeah,
during our session.
no problem.
So good afternoon, participant, and all of you. Now today's is our last day of FDP, and this is our 11th session. Before starting this formally the session, I would like to introduce first our speaker, Dr. Dattatreya Parle. Dr. Dattatreya Parle has completed his graduation from Maharashtra in 1999. Afterward, he has done his MTech from IIT Bombay in 2002. Later on, in 2016, he has completed his PhD from IIT Bombay. His career track record is like this. Initially, he has joined as a junior research fellow at IIT Bombay. Afterward, he joined as a scientific officer at BARC. Then after as a senior software engineer in Geometric, principal consultant in Infosys, technological expert, the senior practice partner Pro, and right now he is a technical fellow in AI division in nuclear AMRC UK state Sheffield. Apart from this, he has a lot of his own technical skill. Over the period of time, he has acquired the skill in Industry 4.0, digital twin, autonomous vehicles, artificial intelligence, generative AI and LLM, databases, data analytics and visualization, virtual reality and augmented reality, image processing, cloud platform, 3D printing, PLM, SLM tools, programming languages, source code management, project management tools. With this, he has also attended many professional trainings and acquired the skill. Latest training what he has got for self-driving car and many others like data management with SQL and DAFI technical training, etc. Apart from this, he has a more than international publications in his credit. Uh, Yes, of course, he has attended lot many conferences and presented the paper in conferences. He has credit, award, recognition, and honor. Very long list is there. If I read it, it may take 1 hour. So, sorry, Doctor. I will just wind up with
Yeah,
only
thank you.
speaking that you have
No problem.
recognition and honors more than the 2020. I can read here from your CV.
Yeah,
Uh,
yeah, thank you. No
So with
problem. Thank
this, I would like to end up your introduction. Thank you very much.
you.
This is very brief introduction. So
Yeah,
now I hand over the sessions to Dr. Parle. Dr. Parle,
thank you.
please.
Thank you, Dr. Piyush sir, and it is nice meeting you online. And just for the audience purpose, we did the PhD under the same professor, same guide. So we have the long association, but probably first time online we are meeting. We used to meet a lot physically in IIT Bombay lab. So thanks, Dr. Piyush, for inviting
Welcome.
me and giving me this opportunity. So I'll try to next probably 80 minutes. I'll try to talk about a lot on digital twin, but I'll start probably. I hope my screen is visible, and I'll go through as much as can possible. But feel free to contact or in between if you have any question, participants. Feel free to uh, ask. Just I'm okay with if you want to ask in between or if you want to ask later. Feel free. Don't hesitate, and I'll try to cover as much as possible. There is a lot I have done in this area, but even if I'm not able to cover something, probably you can contact later. My email and India, that's India number, but it's WhatsApp still works. So India email also I have given. So it's fine if you want to contact for anything. So I'll just briefly go through some of the capabilities in this area of digital twin, what I have done in the past in different organizations. Maybe a lot of that has been covered by Dr. Piyush in the introduction, and then maybe I'll build it. I'll take a step back. I'll build it on IoT. So I'll start with IoT, then I will go into the IIoT, and then the recent trend in IIoT is a digital twin. And then we'll talk in during this, I'll talk about different use cases of IoT, IIoT, digital twins, some of the research, cutting edge research we have done, and some of the standards, some of the practices, all that. And at the end, probably I would like to talk about if some of you want to build a digital twin in the academic labs, how you can get started with devices like Raspberry Pi, and then we'll conclude. Probably that's the agenda here. So there is a long list, and we'll see how much we can cover. Uh, yeah, my brief introduction. Yeah, Dr. Piyush already covered it. I'll not really go more detail, but yeah, I'm academically I'm more into mechanical manufacturing specialism, but professionally more on hardware, software developments, different industries, worked across different setups like research, IT companies, and then once again back to the industrial research. And during this process, I have been working mainly, I mean, I'm fortunate to get into more of the emerging technologies like right time into the technology which is probably emerging. Like now currently I am a tech fellow of artificial intelligence. Earlier I was working in self-driving or what you hear today, robotaxi or self-driving car or autonomous vehicle. I was working in Infosys and Wipro. Maybe then I was working in Infosys Wipro. Along with that, I was working on Industry 4.0 and digital twin. A lot of that context will go there and what I'm doing currently. And then a lot of these days I'm more focused on this what you have seen, tools like chat gpt, llm, generative ai, that kind of stuff we are doing. So that's the kind of, so generally speaking, I generally try to divide my skills into three categories. The core engineering, that's our what I have been doing more into cad cams, PLM and those kind of areas, and then emerging tech like VR, AR. One point of time, I was developing my own VR headset. This is a 3D printed VR headset, and then Industry 4.0 3D printing. I had my own startup in India when I was in India on using 3D printing, and then a lot of software development I have done. So I'll touch upon this later also, but just to give a flavor, the current and future trends in industrial IoT. So that's industry 4.0, but already we are still maturing in industry 4.0, but the people are talking about industry 5.0, and these are the some of the skills which are required in industry 4.0 and industry 5. All the skills I have worked except this red cross, and currently I am more working on digital twins and artificial intelligence. I may not talk much on artificial intelligence today, but I'll talk a lot on digital twin because that's more aligned to today's talk. So we'll discuss more about this later. So just to give you another deep dive on that kind of experience which I have built, say autonomous way robots. Currently, we're trying to build our own autonomous robots. I have done a lot work on simulation, system integration, IoT, cybersecurity. We did a lot of research previous years, cloud computing in Infosys and Wipro. I'll talk about these case studies. Additive manufacturing, I had owned my setup. Then VR, AR, I was leading this practice in Infosys. So a lot of those pillars of Industry 4.0, I was working across. And more of my role have been R&D led work. So the focus was building the services in companies like Infosys, Wipro, and my own startup R&D led service offerings. So we had built R&D led service offering VRAR, which is another pillar of IoT. We have built autonomous systems. We have built medical device service and so on. And then digital twin. We built a digital twin last year in nuclear AMRC in UK. So that's kind of thing. And as I said, a lot of work I have done in a VR AR. I had my own VR headsets. I was a kind of Amazon entrepreneur when before shifting to UK. And then let's get started with the fundamental topic of the today's talk, that's digital twin. But how digital twin has come into existence, where it starts. So it probably starts with IoT. What is IoT? Internet of the Things, probably everyone knows and everyone probably is using it today. What's the since I mean in IoT, probably I'm now working almost more than a decade now, and there are uh, I suppose some of the reports there will be billions or trillions devices will be connected in next probably 5 years to 10 years. And today already we are seeing that our world is connected. Our world is connected through smartphones. We are now connecting smart homes. We are connecting to everything. So our televisions are getting connected, our mobile phones getting connected, our emails getting connected, our travel getting connected, our health getting connected, right? So everything is getting connected. So IoT has become now the mainstream, and that's trying to, so it is the era of internet where we we started with the internet probably 2 decades ago, and then we started connecting that internet to the things, and that's what is IoT. We are trying to connect it to the internet, to the physical devices, everything around us. As a human being, we were using it earlier. Now we are connecting it to the devices, everything around. So today, I need not to give any example probably for that, but everyone is using some sort of IoT device. Without IoT, our life is incomplete today. So there are, say, smartwatch. If you are using smartwatch, probably you are using IoT device. Or if your TV has smart connectivity, probably, or if you are using some camera in your home, probably, or in your lab, probably, or if you are connecting to some smart app or something through sensors or computer vision systems or through the internet, then you are already using some sort of IoT device. So what it involves, IoT, how it works, probably, it is a fairly four-step process. So there are sensors. right? They are collecting data, they are connected to the internet, sending, doing that processing, sending over some user interface, right? So earlier also we were having, let's say when I was doing my master's project, I had a lot of sensors on my welding machine, but we never called it as IoT. Why? Because we are not connected to the internet. It was just a system with sensors, but not connected. It was a local system which can do that. But now, when we are trying to connect those sensors or that devices connectivity to the internet and then doing a lot of data processing to make a meaningful decision and then presenting it to the user in a more meaningful manner or more actionable manner, then that's what is something called IoT. So IoT, that's how it works. You need these four things. If you don't have these four things, probably any one of the thing missing may not qualify it as IoT. Think like connectivity. You have a sensor. That's what I said. I was having, let's say, if I look back my master's project, where we were trying to mount multiple sensors on our welding machine and do some processing and then do take control that robotic path following. We were trying to do autonomous path following of the welding machine. That it was missing second block, that's the connectivity, right? We were doing data processing, we were using sensors, where we created some plots and all that, but that's definitely we can't qualify it as a IoT. So if one of the block is missing, probably we might still not qualify it as a IoT. So typical IoT, I'll revisit this again and again several times. So typical Internet of the Thing architecture for any system, if we look at, I just elaborated these four steps. Interlayered architecture, that's a physical layer. So you have the sensors, that's a physical layer. Physical things and sensors together we call physical layer, and then connectivity layer, that's the second block. Now what it can have short range connectivity, long range connectivity, very long range connectivity. Is it a cellular connectivity, or is it a Wi-Fi, or is it some sort of other communication mechanisms, right? And then there are several communication protocols get involved into that, and all that need to be addressed. And then if you go into the third block, that's data processing, where you have to do, once you have connected sensors to the things and communicated that information, but the just, if I, let's say, start collecting some information using some sensor, but if I'm not really able to manage, process, and draw the insights out of that, it doesn't have the meaning, and it all needs a lot of things to do. That's what we call a platform layer or data processing layer, whatever different terminologies people may use, but that's what is. That's a platform layer. And then finally you present that information in some meaningful manner as a report, dashboard, or controllable action, actionable controls, whatever it is. All that comes into the application layer. So that's how it works. And this is a very fairly standardized layer wise architecture which needs in IoT kind of applications. And now some of the use cases, I'll take you back. These are some of the examples which we worked in Infosys as IoT. When IoT started a decade ago, or probably 15 years ago, this IoT buzzword started, and I was working in Infosys, and then we started using a lot of ways IoT. Now this was one of the use case where a customer wanted to build a solution. This is an insecticide manufacturing company. They they wanted to build, and those days, probably if I remember, in 2014, 15, 16, that was the era when we used to hear a lot about Zika epidemic, which later, maybe 5 years down the line, we had this COVID, which was a much more severe. But there was some lot of tension about this disease, Zika uh, epidemic. People were worried too much about this, and some of the companies in US were working on building a solution to control this disease in a public places. And this company was a insecticide pesticide manufacturing company which wanted to build a solution. And now countries like developed countries like US and some of the European countries where the large public places and there is a labor challenge where you don't get often deploying manual labor is a more costly in these countries. When I have shifted in UK last 5 years, I can see that the preference is always doing it things through machines, automation, and all that. So this company wanted to build a solution, and they came up with the requirement of what we can build, say for a public places, and which we can autonomously control the Zika. Now, I was not really aware how Zika spreads, what happens, and all. I had to really do what I had to do is I had to do a lot of brainstorming with the doctors, because when this requirement hit to my mailbox, I was first question was where I start, and then the first thing came to my mind is when I learned about it is that this Zika is caused because of mosquito. Then first thing hit to me was, oh, in India, in the past, we had a lot of mosquito-borne diseases and like malaria epidemics and all that, right? So then I started talking to a lot of doctors and I understood how they used to control, what the measures they used to take. A lot of some government doctors and my family itself, my in-laws, all in-laws are doctors, so that was a blessing for me to get this into that. And I asked my father-in-law, who's serving in Maharashtra government, and I asked him how they used to do this. Uh, and then he explained the whole process of mosquito-borne disease control, how they used to do in the past. And exactly same thing I tried putting into the IoT framework. What he said is, okay, they used to go places, check the type of mosquito which are causing malaria, and then take the samples and then try to do the pesticide and insecticide, lot of that, and sprays and all that. And then when I understood that whole process, but it was a manual, and then definitely that really doesn't work. And then the same thing which I felt would work in autonomous way using some of the technologies, that's IoT. I proposed it to the customer, which was demonstrated in Chicago workshop by the customer, where what we said is we'll deploy some high speed cameras and high quality cameras, sensor systems, and then maybe some sound sensors also we propose. But the primary first step we wanted to deploy was a lot of image acquisition devices. We'll monitor two things. One is Zika causing mosquito type. It is a typical mosquito. Not all the type of mosquitoes cause the Zika. And then we will monitor two things: a type of mosquito and the cluster of mosquito. How many mosquitoes are the density of the mosquitoes. And then the moment we see, we will keep the counter of the Zika causing mosquito, and then if we see there is a lot increasing, probably just release the insecticide or pesticide, whatever the spray that company was manufacturing to control the mosquitoes. So that's probably one of the use case I worked using IoT. And similarly, then I came across in similar period of time, if I remember, again there was a company who was manufacturing the diapers, and that's what I said, right? My role was R&D led role in many companies, where and many times when such requirements used to come in a more vague manner. So this was a diaper manufacturing company, Kimberly Crall. So what they said is they want to build a solution. And those days I was working on this virtual reality. Some of the emerging techs I was working, virtual reality, augmented reality, and IoT, industrial IoT, and all that. And that's where this requirement came to my inbox again and said, this is a diaper manufacturing company which want to build a solution, a smart diaper. They wanted to build a smart diaper, but then they don't know how what they want exactly, or they don't know how it can be done. So primary role was to do some R&D and identify how what is that smart. Those days even smart watch was not even much heard, right? So people were just trying to make IoT and all that. So I was like, okay, maybe let's try to understand how to make this diaper smart. Again, maybe my wife is, again, my family comes to my help. My wife is a pediatrician, so it helped. And those days only I had my baby, which was she was around 4 5 years, and then she was still wearing these diapers, and also product was very familiar. So then we were thinking, I was just started thinking how we can build, how we can make the diaper smarter. And that was a big challenge because diaper is use and throw piece, and you can't make a smart product and throw every day, right? So we really need to think through. And I probably then I talked my wife as a doctor, I talked my wife as a mother, I myself father. We thought how we can make it, and then I thought probably if something I can have some sensor chip or sensor device which can be removed from the diaper and which can be put on the diaper and things like that. And then what sensors we should put, what sensors can be put, how small, how big it can be, is it a hazardous to the baby, is it, all those things we tried addressing. And then we tried, and then the whole purpose was like, now this company has a major business in developed countries again, like UK or European or US countries, where majority focus is, major people use this diaper often. And then the focus is in this country has lot of big houses, different rooms for the babies and all that. So uh, I wanted to build something which can give um, comfort to the parents, relax about the babies. We are often worried about the babies. So what I said is, maybe I coined some word called baby comfort index. So we said maybe we'll monitor several aspects of the baby through that sensor device. And then like maybe we will monitor the activity, sleep. Maybe there will be some external sensors which can communicate to this device like camera, humidity, temperature, and all that. Then maybe urination and type of quality of urination, feeding, all sort of things we wanted to put. And then when we proposed the initial idea to this company, and they were like very much idea, but they said they put a condition that device should be of a matchbox size, then they would probably buy that solution. And then I said maybe that sensor will collect the data, connect it to the platform, and process the data. And then there will build a model, AI model, which will trail what is the comfort index of a baby, BCI. That's a again IoT use case. That's how we started in the early beginning when IoT was just in nascent phase. And then slowly when IoT started growing, then there is a that that IoT was, I was making a lot of impact in the common life, common people lives. Like we were started using the smart devices, smartwatch, bands, go to the shop, and connected vehicles, and a lot of things started becoming smart using the IoT. And that at the same time when that IoT technology started making difference to common man's life, it started impacting the industry. And that's how IoT started making inroads into the industrial industry. And that's how the industrial IoT came into the picture. So the Technology is same, technology is same, but business drivers are different. Technology is same, you have the sensors, you have data processing, you have visualization, those four steps are same, right? But one is in industrial context, one is in a consumer context. In a consumer, what we want is a probably more we are worried about the quality of life, security, cost, right? But in industry, we are more worried about quality of service, robust, secure. We want secure, right? Robust security. Not maybe at a user level, we are still okay. And then if I deploy some technology in an industrial setup, I am always worried about is it going to pay me back or is just an investment? No industry want to do any investment without the ROI. And then are we will it be in terms of efficiency? Can it bring new products? Can it make new markets? Whatever it is. So same technology, sense devices, sensors, connectivity, data processing, and visualization, but drivers are different. And that's how slowly, with the rise in IoT, things have changed in the industrial setup. And IoT led to something called digital transformation in an industry. So today also a lot of buzzword, lot of industries, not just. I was thinking before moving to UK, I was of the opinion maybe probably lot of industries in UK might be state of the art or. But when I visited some of the industries here also a lot of industries are still manual, needs a digital transformation. Small companies or even medium companies are still do a lot of traditional work. I mean, I last month I was in one of the company, which is a glass manufacturing company, and I really felt am I in India because I used to see that kind of work lot of manual work in Indian small or medium companies, but the same is also here. So digital transformation is still big thing in many companies across the world. So deploying technologies, data, internet, IoT, or automation, or AI. Now with the rise in AI, a lot of companies want to deploy the AI, all sort of that digital transformation. So everything we want, whatever we are doing manually, people want to convert into a digital, and that's a big thing. And one of the driving technology for that was a IoT, and that led to the rise of IIoT or industrial IoT, which we started calling Industry 4.0. So now what's that Industry 4.0? Industry 4.0 is the fourth revolution of industrialization. So we know first revolution of industrialization from the history, right? Somewhere probably 18 so probably 18th, mid 18th, okay, 19th century probably, where we started. Earlier our manufacturing was using a manual labor, which we converted into the mechan mechanisms. A lot of mechanisms started we using with the and but then when we started that industrialization, then we started producing more using mechanisms or machines, but then that was not enough. That needed to be, the market consumption was more. To meet the market consumption, there was something needed that's called automation. We started using a lot of mechanical automation to produce more, and that's the second revolution of industrialization we call. And in the third, the ones we started using machines, then we started using mechanisms, automation, and all that we started. But then with the rise in computers, electronics, robotics, industry started deploying these devices, and that was the era of industry 3.0. And we were living in the, probably most of us, we lived in an industry 3.0 era before we professionally started our careers. And that was the era industry 3.0, where a lot of electronics base, maybe a sensors or maybe automation using electronic systems, robotic system, computer systems, we started deploying. Now, in last 2 decades, there is a boom in internet, 2.5 probably, and then in probably more than 1.5 decade now, there is a boom in IoT, and that led changed the way industries work today, right? And we started connecting these industries or machines or equipments or systems of an industry to the internet, along with all whatever you had, the mechanical automation or robotic automation or electronic based automation, and that's what we call now. So this probably in last 1 decade probably you started hearing more on something called industrial IoT, IIoT, industrial internet of the things, which is also interchangeably known as the industry 4.0, and that's what we call the fourth revolution of industry. Now, and these are the pillars. Generally, these are the technologies which enable the industry 4.0. These are the 9 technologies, and you may have all of these, or you may not have. It doesn't mean that if you don't have something, it doesn't become an industry. Maybe maturity level of industry 4.0 will change, but essentially you need some of this technology to ensure you are moving towards the industry 4.0. Definitely IoT, then along with IoT comes probably integration, maybe it comes with simulation, data analytics, then security, VR, AR, maybe autonomous systems, robotics, cloud. All these technologies inherently start coming the moment you bring the IoT into the industrial setup. So just to talk about that this is a slide which I talked, right? So I was doing a lot of this simulation earlier. My PhD itself is in a modeling of microstructure, and then I did a lot of, say, this is a recently we did simulation for ultra MQL, that is a try to minimize the lubrication into the machining operations. Then we did some simulations on uh, uh, additive manufacturing, how material deposition happens and all that. And then in this is something which I was doing a lot in autonomous systems in my BRC, and we used to do a lot of system integration across the industries. Then we built IoT or industrial IoT case in, this is a welding. I'll talk more maybe later. Then we did last year, we did this research into the cyber security in the nuclear and defense sector. When I was working in Wipro, we were building this digital twin on the Azure cloud platform. And then I was building this VR, AR systems. I had my own VR, AR products. Probably I have not done something is more of big data and all. I was building these autonomous systems. Autonomous self-driving car engineer is a certification which I did for. So a lot of this experience I have been working all the bits and pieces of, and then we built something called Industry 4.0 use case. That was the first when I implemented some of the IoT use cases in Infosys. Then we built. I was also part of building this Industry 4.0 use case, and I'll talk about that. So this is a recent one. I was showing earlier slide, right? So this is what we had done here in nuclear AMRC was uh, building this automated welding equipment system, inspection and monitoring, AUSIM, where we had deployed 3 sensors. One is vision sensor, camera for external defects, then laser sensor for profiling internal profiling and external profiling of the weld, and then ultrasound sensor again for the internal defects. And this was more real time industrial IoT setup where we, and then we also built some additional AI/ML models to identify whether the welding is good or there are some issues, because it is a multi-pass welding and is a nuclear the huge component which is typically used in a nuclear plants, and which has multiple, and we wanted to do multi-pass welding, and we wanted to ensure that this real-time defect identification and classification can be done, and so that the corrective action can be done. You can see here, right here, if you see here this profile, laser profile, here you can see the ultrasound waveform, and this you can see the images, right? And then you can see the AI based visual inspection, which will tell weld is good quality or needs the cleanup or before the next pass, or is it a bad quality and needs change some parameter before it really proceeds. This kind of use case we built. Then this is then I'm going back long ago, probably 10 years ago, we started building something called uh, uh, industrial IoT. When we were working a lot on IoT, we started working on industrial IoT, and we built. Now Infosys has multiple offices, as you know, and then we started building that IoT solutions to various systems of to make the sustainable building sustainability initiative, and where we deployed sensors into the light monitoring, AC monitoring, chillers and data centers and heat treatment plants, sewage treatment plants, and all sort of that. And then we build this centralized command center from where we will know which building is having what sensors, what the consumption, and all that. And that's something we used to demonstrate to a lot of our customers. And then we also when I started working in a VR, we started building VR enabled solutions also. And then it has shown those days probably deploying such probably 46%. So that was a industrial, although it was not a truly, I would say, not an industrial setup, but just to show the capabilities and just to show the benefits what we can obtain in our Infosys industrial equipments. We used to do that, and then we used to showcase how it can be done for the predictive maintenance or different kind of managements and fault findings or visualization and all that, how it can be controlled remotely. Let's say the centralized command center could have would be operated from the Bangalore, and if there is some system in Pune building which is having some fault, can be remotely switch off. Let's say I see some air conditioning in the plant in the building one is not working, probably we can just take some corrective action remotely. That kind of solution was built. And then also we participated, myself and other team members, we were, because as I said, most of us lived in industry 3.0 era, and we are now in industry 4.0. And now there is a still lot of companies struggling to get into the industry 4.0. And then there is as a company, I don't know whether what I should do, whether what is the maturity of my industry to go to deploy this industry 4.0 solution. So what started we built a framework by collaborating with University of AICTE Germany, that what how do we assess the industry's maturity to deploy the industrial IoT solution, and what it takes to do that kind of if you search industry maturity index Infosys and Architect, probably you'll come across some report. And then we used to then say, oh, this industry is at this state, and what benefits you get when you move from connecting, visualizing and predicting and adapting those kind of maturity levels we defined. So in general, there by now you probably understood what the industrial IoT is, and industrial IoT in the manufacturing industry has a lots of applications. Okay, just to take a example of automotive, this is user side, not industrial side, right? You want to connect the cars, you want to do this autonomous vehicles nowadays. You might be hearing a lot about the robotaxi. So all that what is nothing but a industrial IoT use case from the user's point of view. So all these are from the user's point of view in vehicle infotainment, telematics, maintenance, connected cars, fleet management, all that is a part of now user side. But when you go into the industrial setup, how does it help? Maybe it has a various applications across the product life cycle, across the your industrial setups. You can probably start maybe asset utilization. You can track your machines, equipments. You can do the environmental monitoring. You can do energy consumption. Probably I'll talk one of the use case which work on energy consumption, and then fault detection and predictive maintenance, real-time optimization, quality checkups, supply chain management. Where is your this is one of the use case we are trying to build it for the smart port, and then quality checking, route planning, real-time monitoring, then product monitoring, logistics, quality, inspection, demand, all that. Workspace safety, monitoring the personal environment, how they are operating, whether they are doing proper job, all that. So there are lots and lots of applications in industry for industrial IoT or industry 4.0. So although we are still we have not completely matured in industry 4.0, but already there is a talk being of the industry 5.0. So we already mechanization to electrification to automation to digitization. So we are the in era of the digitization and moving to something called the personalization. So that will be the future of industry. Now, within this industry 5.0, or maybe this digital twin comes in both, is one of the emerging trend of industry 4.0, or maybe we can put it into industry 5.0. That's because it is a personalized. Now, human machine collaboration. Here we are just talking about digitalization without human factor, but here in industry 5.0 we are talking about focus of human machine collaboration. In the industry 4.0, the focus was on a technology, deploying the technology to reap the benefits. Whereas we are talking about, yeah, we will deploy, we make industry 4.0 complete, but where is the human and how they will collaborate? That's what something we are talking about now. AI, cobots, blockchain, digital twin, meta, that's VR, and 6G. We are yet to realize the benefits of 5G, but we are still now we are moving with the quantum and 6G and all that. I have probably not worked on these cross mark areas like blockchain or quantum or 6G, but most of the other technologies I have been working in some or the other form in some companies, and different use cases we have built. So if you see the three horizon model developed by McKinsey, in the connectivity, which probably more relevant to industry 4.0 and industry 5.0. So existing market is still, we are still industry 4.0 where we are trying to deploy these technologies, but the emerging trend is digital twin, and that's what is a lot to talk about it, and I'll be talking about that. And then in future probably we'll have this industry 5.0. So we also built a connected platform at Nuclear AMRC when I joined Nuclear AMRC 4 years ago. And we built this platform to monitor all 3D printers across our facilities. And it has a capability to connect. We were monitoring almost 100 plus data points. More than it has a capability to bring 100 plus printers on that platform. And we built this proof of concept through the government of UK catapult funds, and that led us to build several other solutions. So that was again using the same, 4 layers of solution, something similar what you see here now. Then because I was working in nuclear AMRC, so we were working a lot of work for nuclear decommissioning. So this is one of the use case we built for nuclear waste management. So where they wanted to, so this is a physical layer where this waste management devices are there. We wanted to build now deploy a lot of different sensors. Already there are a lot of sensors, and then this is something called melter, calciner, and scrubber, and different kind of mechanisms. They do the processes they do with the nuclear waste, and then deploy it, bring that data to the cloud, do this ontology building, that knowledge graph building, build some AI solutions to do various activities like tracking, monitoring, prediction, fault detection, safety aspects, training using this kind of devices, and then build some state of the art 3D visualization, 2D visualization, AR, VR, and all that. So physical layer, communication layer, digital layer, and user layer. So if you look now, so this is a more of a something I'll call not industry 4.0, it is more of now digital twin. We are already now, we are moving from industry 4.0 to digital twin. So this is a, again, although it is a industry 4. It can be into industry 4.0 or digital twin. So where, but the fundamentals remain same. So if you look back, IoT, it has the same 4 layers. If you look in industry 4.0, it has a 4 layers. Now, if you look into the digital twin, it has a 4 layers. So we proposed this digital twin for smart port. So there was a challenge by Port of Tyne, which they wanted to address the smart logistic operation of a port of Tyne, and they have narrated. So this is a high level solution which shows what is the state of art possible, and they suggested that all assets are not tracked, so they do a lot of vessel operations, warehouse logistics, cargo handling, there are cargo equipments and other activities. So they said they are all not tracked, there are limitations of RFIDs, they are they are already built 5G but it is underutilized, and then there is a congestion, labor shortage, delays, inefficient utilization. Lot of these challenges they wanted to address through the smart logistics system, which we call smart port 4.0. And we suggested step by step approach that we said we'll study the current status, identify the assets and sensors, build connectivity and communication systems, and build a platform layer, deploy the digital infrastructure. So sometimes this industrial IoT or maybe a digital twins are also called as a cyber physical systems or digital replicas, all that. Probably I'll go more detail into the, but so it is a cyber physical, so industrial IoT is a bigger one, let's say a larger umbrella. CPI is probably a part of it, cyber physical infrastructure, and then digital twin is a sub part of it. And then we said we'll build that, study the current, all your equipments, identify the what are the challenges, how they operate, right? Your logistic system will deploy design thinking approach, and then make a list of what need to be done, and then we build a physical layer. Then we'll identify the critical assets, identify the sensors, what are the existing sensors there, which needs upgrade, and all that. Deploy, we do the 5G connectivity, compatibility of the sensors, and then do this, build a physical layer for all then making this sensor selection using some potato plots and spider plots, all that, and then uh, do build this communication layer using 5G, because that's something they wanted to utilize using various protocols. And once you do that, then build this, design, develop, and deploy this digital layer. Digital side, we are talking about so we can build these data lakes, data warehousings, connect to ERP and other CRM platforms, which cloud, on-prem or public or hybrid, all that we'll be doing. And we backend, probably we need to have these knowledge graphs, AI, to do this real-time tracking, asset utilization, efficiency, net zero operations, and all that. So that's something. So if you can see, probably I have been slowly moving from IoT to the industry 4.0 to the cyber physical infrastructure to the now digital twin. So maybe in now the last part of the talk is more on focusing on the digital twin, and I'll talk more digital twin use cases. So what is digital twin? Is a digital replica of physical product, service, or process, anything. That's one thing. In the simplest language, probably we can call. And there are a couple of papers we publish, and one of the paper probably will come across. We mentioned there are lots of digital twin definition. There is a lots of one of the research paper, probably review paper, I have listed 18 digital twin definitions. So, but in a simplest manner, we can call it as a digital replica, whether it is a physical, any product or system or service or a process, anything. So it can be anything which is a digital, which has a something physical, whose mirror of it, which is represented digitally, can be called a digital twin. So digital twin, we have garnered significant interest in the last at least 5 years or more. And I myself is working maybe more than 5 years now in digital twin. Earlier, probably we used to call a lot of industry 4.0, but since last 5, 6 years, I have been talking, or I have been significantly, proposing to build a digital twins. And one side there is a real world, on the other side virtual world, but both are same. So we measure the data, we do the back and forth communication in digital twins. So there is something called digital twin consortium, which is a body which maintains this digital twin definitions and capabilities. So they've listed some definitions of the digital twin, and they also listed what are the characteristics or categories it will have in the digital twin, and they came up with something called periodic table of the digital twin. Okay, they came up. I'll talk about that. But then, what is digital twin market today, right? I mean, so as I said, IoT is increasing, industrial IoT is increasing. It means the connectivity is increasing. So digital twin is increasing. So Gartner, which is a market survey companies, which publishes several reports every year. So they published a report earlier in about a decade's digital twin market, and they said probably digital twin is the top 10 technology trend will be there in the industry, which will grow around 30%. And because the billions and trillions devices will be connected in future, and and that is why probably it has garnered that significant interest since last 5, 6 years, and this will be still there in another 5 years minimum, I will say, until you come up with something disruptive. Uh, Now again, if you see the architecture wise, it is same. IoT, we talked about the 4 blocks. In industrial IoT, we talked about the same 4-layer architecture. And in digital twin also, it is the same. So the fundamentally, it remains similar, but there will be a lot of enabling technologies. So this digital twin consortium came up with something called periodic table. They started calling CPT, and they defined 61 capabilities that completes, state of the art digital twin, which are divided into 6 categories. That is a device management, integration, intelligence, trustworthiness, and user experience. So which is something probably we can call probably a 4-layer. Instead of 4-layer now, you can call a 6-layer. But I would still, to make it easy, I would still refer to the 4 layers of architecture. This within these 4 layers, probably these 6 categories fit. And then they also further they created more like a periodic table kind of structure. I have given the website here. Maybe if you go there, you'll come across. So all these device categories, then integration, management, then this is trustworthiness, this is user experience, right? And this is the intelligence. So within that, you can have a different subcategories, right? What are the data or integration related capabilities? What are the device management related? What are the intelligence related capabilities? The digital twin should have, or digital twin can have, for building a more structured approach, taking the structured approach, building the digital twin in the industrial setup. We don't want to build something, that's what I'll show you one of the example where we're trying to build digital twin platform for one of the petrochemical oil and gas companies. So because we don't want to build one, or don't want to build every time a new digital twin and do the same effort. But if you follow some structured approach like this, then you can make that a common framework which can be reused again and again to build it quickly or deploy the digital twins quickly. So that was the purpose. So this is one of the use case. Maybe let me see if I can play this video. Uh, yeah. So this was one of the use case we built, which has all those
Hi,
technologies.
my name is Kevin
I
Donnell.
hope the
I'm
sound
an
is
experienced
visible.
design lead here at Infosys. What we have here is a 3D printed aircraft jet engine. It's an open source model that we've made a couple modifications to. This is an IoT use case for our artificial intelligence platform with large industrial assets. Myself and 2 other VR experts spent the last week and a half developing not just this model, but an entire augmented reality overlay that goes along with this experience. So with this 3D printed turbine, we have a couple sensors on board. There's a strain gauge sensor to measure the deflection of the plastic. There are temperature sensors to measure the temperature of the combustion chamber, where one of the 2 engines are lying. And those 2 engines on board, each of these 2 engines drive the separate spools on board this engine. So all of these sensors are collecting data, feeding this information up into the cloud, and then we're able to grab that information from the cloud with the Microsoft HoloLens and display that information on top of this jet engine turbine in a contextualized manner. The strain gauge will show a blue-green heat map overlying the deflection of the plastic throughout the casing of the engine. The temperature sensor will give the user a red-orange stratification of the temperature through the fan section up through the combustion chamber and then down into the turbine. And the user is also able to get information on speed throughout the different blade sections. Additionally, there's a one-for-one digital representation that is built of this exact same model, which is a digital twin of this smaller 3D printed jet engine turbine. We're able to leverage prognostics, scroll out 1 to 2 years out into the future to understand what this turbine would be experiencing if we continue to run at this specific duty cycle. We can then break down this larger engine into very specific components, all of which make up this very complex model, and understand root causes of specific failure points that we might be able to determine 1 to 2 years out. We can then use that information of this knowledge model to teach people how to go in and service large assets like this turbine. And so this can be applied to many other large industrial assets. Anything that has a surplus of sensors, information coming off of it, we can introduce this new way of how these things are going to react downstream and better prepare for servicing them in the future.
So that was one of the use case we were working when I was in Infosys. And then when I was working in Wipro, then we started building this digital twin platform because they realized everyone is building digital twin in British Petroleum, and it is again the rebuilding, everything is rebuilding. So can we build a framework? And that's what we are trying to build. So we are building a digital twin platform in the Azure, and we were trying to stream the sensor data, build that knowledge graph, and then visualization and all that. And can that be reused again and again? So we are trying to do this for one of the their oil extraction site. That's a clear read. Maybe I'll just play what that was about. Maybe you can get the scale, what the scale that oil extraction site has, and then you will understand why it is needed building that, that kind of digital twin makes sense. So you can see the kind of assets they have in the oil extraction in the sea, and it is a having the digital twin which can be seen, which is available from anywhere, remotely, will give a lot of insights to the uh, companies, because you can imagine this is a huge drilling body. Is it 50 meter by 50 meter? You can imagine, 40 meters, then 10 meter high. It's huge, and there are a lot of, you can see the equipment and lot of systems which need to be monitored, tracked, and if you can predict what can happen in the future, and that is what we are trying to do, we tried bringing this whole 3D visualization into the digital tool with a lot of sensor information, and then making it more useful for predicting the faults, what is the current asset status, health status, what all those sort of things, building the some AI ML models and all that. That's what something we're trying to build. So I'll not go into that detail. I just wanted to give you the flavor of what you know what was that kind of assets we are trying to build. Now, this is another use just to understand, how the Microsoft Azure can be used. But in the interest of time, probably not go into this detail. But if we get time, probably I'll just play that later. But I will go into some of the works which we have done again, some of the use cases. So in the nuclear MRC, when I joined maybe 2021, I started working on building this digital twin framework. It was again funded work by government of UK. We call it as a catapult fund. And then we also got another fund for cyber physical infrastructure characterization, standardization. I'll talk about that also. So again, we propose that this was conceptualized by me in Infosys, which I carried in Pro, and once again we carried in nuclear MRC, a 4-layer architecture: physical layer, communication layer, platform layer, application layer. What are the physical assets are there in nuclear MRC? What are the communication protocols that can be used? What kind of platform layers we can build and visualization layers we can have? what is the current data flow in the nuclear MRC. That's very complex, which is not straightforward. You can see, right? Data is stored locally, data is there on some network devices, share points, some storage, and users are accessing it randomly. The assets are not streamlined, not going through. So for building a digital twin, probably you need a more streamlined approach. And that's some of the things which any industry, when you want to build a digital twin, you need to study that. And the next part, what we did is we built something called cyber physical uh, infrastructure characteristics. We realize within the UK, again, industries, a lot of industries are far behind to adopt this digitalization. And then we wanted to build a framework which is more focused for the manufacturing industries. And you can see here also, it is a focus is more that now we propose in a 4-layer architecture. More it is a, now instead of calling what I generally used to call the report in this report, and this was again a large consortium across the probably 8-10 organizations together. We collaborated to build this framework. So again, the nice thing to note about is it has again those 4 layers. It is observable manufacturing entity, which is more like a physical layer. Communication layer, this is a communication layer, and this cyber entity is nothing but that platform layer. And then there comes some cross entities which probably my architecture doesn't address. And then there are user entities like interface, UIs, and all that, but it remains the same. The approach probably is need to be adopted is similar. That's the high point I wanted to. Then we got some research board funds when I joined. And because when I joined in nuclear MRC, there was a lot of focus was on, now in UK there is a lot of focus on this net zero sustainability, because UK is one of the first country which has committed to be, carbon neutral by 20, I think 2050 or 2040. And therefore the government these days releases a lot of fund, and there is a lot of emphasis how can we minimize the emissions. And when I joined, I joined as a tech fellow for artificial intelligence. But the focus, because there was a lot of focus on that, then we thought how AI, how this digital twin or industry 4.0 can be utilized for making the industry's emissions minimize or make neutral. And so again, we wanted to make a plug and play digital twin platform, because we can build, everyone can build a digital twin platform, but we don't want everyone to start from the scratch. We wanted people to use, streamlined approach and plug and play. So like the in the home, when you bring smart TV and you just connect it and it becomes smart, there is no hassle to, so that kind of approach we wanted to take. We wanted to have this physical system as simple as plugging the sensors, and digital system, the moment we connect the physical sensors, just do some configurations and you get that digital twin. So if that is there, probably a lot of companies will adopt that digital twin, and that's what we built. So what we tried doing is, we said you identify the sensors, you identify the assets. In the back end, whatever this, and we will provide you an interfacing tool, something called a configurator, and we will build something, the visualization and digital twin, digital side of it. So this digital, if you go back here, this digital side of it, this is a physical side. You just identify the asset, mount the sensors, do the configuration through the configuration tool, and digital side of it will get created automatically. And that's the plug and play approach we suggested. And maybe, and the architecture within that was built in such a way that it was again a layered approach. Every layer is a twin. So twin for organization, twin for facility, twin for space, twin for asset, twin for everything. And we just connected all these digital twins to make it a more work in a more plug and play fashion. And the focus was here for net zero manufacturing. So we were just trying to get that energy consumption or waste management, all that. We publish this paper also in IEEE, and maybe I'll play the video in the interest of time, and then you can understand more.
The plug and play digital twin for net zero manufacturing is designed to empower manufacturers in effortlessly implementing a digital twin solution for asset monitoring, streamlining the journey towards achieving net zero targets with utmost simplicity. On the hardware side, simplicity is achieved through the deployment of an array of sensors, offering a versatile and streamlined approach. The manufacturer is required only to input essential details into the configurator tool, enabling the automatic creation of comprehensive elements such as data models and interfaces. This process ensures a streamlined and efficient setup without unnecessary complexities. The data is presented on an interface showcasing essential information. The main screen displays energy and carbon data for all manufacturer facilities, featuring comparison charts, line charts, AI/ML models, asset, space, and department counts. Additionally, it provides an emission reduction scope, indicating progress towards the net zero journey. Navigate to detailed facility insights for specific information on energy and carbon emissions across various assets, departments, and spaces. Effortlessly switch between facilities using a drop down icon on the same screen to access data for different locations. From this screen, you can further explore different sections including assets, departments, and spaces where more in depth insights are readily available. Moreover, you have the capability to monitor all assets on a single screen, categorized by facility, department, and spaces. The ultimate screen provides comprehensive details of a specific asset encompassing fundamental energy and carbon usage, along with predictions derived from AI/ML models. Additionally, delve into more insights such as asset power requirements, energy rating, maintenance history, and the monitoring of additional attached sensors. In conclusion, our integrated solution empowers manufacturers with a seamless journey towards net zero, leveraging user friendly hardware deployment, intuitive interfaces, and detailed insights across assets, departments, and spaces for informed and sustainable decision making.
So this was the work we did earlier, and then we are also trying to propose something similar for. There was a one India UK funding opportunity, but we really did not do. We wanted to do this more for sustainability, not just energy based monitoring system, but we wanted to do waste management, circular economy, resource efficiency, and all that plug and play. Somehow, due to lack of partners, both the side we really did not apply. But there are opportunities to collaborate. India, UK, we have to just keep watch on uh, when the funds are there, under which headings and all that. So maybe if some of you come across something which is India promoting or looking for India UK collaboration, I'm happy to talk to you. And if I come across, probably I'll try to see. I try to contact some of my friends in India, but this is what we were trying to do, but we have not really done. So then earlier when I was working in Wipro also, we published something called this white paper, which is called Digital Twin Taxonomy. So if you might you might have seen that, right? Or you may have heard, you will come across a lot of, there is overviews of digital twin terminology. There's I would say probably overuse and glorified that terminology with the, and that is underlying the because of that its underlying meaning has been diluted. That's another problem. And that happens with any emerging technology like today AI/ML, right? Everyone starts calling AI/ML, everyone starts calling digital twin now. So that's the problem. Any IoT, everyone starts calling digital because that's an emerging trend, right? And but it dilute the underlying meaning. So therefore what we thought is we wanted to bring some clarity to the industry. That's something, if you have seen that Industry 4.0, we worked in Infosys, which was more on maturity index, something similar we tried doing when I was in Wipro. We tried clarifying that or trying to bring the clarification in the overviews digital twin definition. So what happens is when people started with the digital twin terminology, people started calling CAD models, simulation models, everything as a digital twin, but it's not really a digital twin. Or then there is a interchangeable terms like virtual twin, digital replica, digital twin, virtual design twin, operation twin, and lots of that started coming. So that keeping in that mind, we thought for both users, manufacturers, designers, everyone across the industry stakeholder will try to provide a more holistic taxonomy, digital twin taxonomy. We divided into the pre-IoT and IoT era, and then we tried making a more level levels of a digital twin which represent the maturity. And what we did is probably we tried defining the digital twins in a 5 levels. That is level 1, level 2, level 3, level 4, level 5. Level 1 is more like we said, okay, maybe a CAD representation we can call a level 1 digital twin. But if we have, say, CAD and CAE or CAM together, maybe if people want to call a digital twin or virtual twin, maybe they can be level 2. And now you put the sensors, IoT, a simple IoT, still not a digital twin, but we can call a journey towards the digital twin a level 3. This level 1 plus level 2 or level 1 or a 2 with the sensors is a level 3. And now when you have level 1, 2, 3, can we have now prediction models? Can we have more, actionable insights? Can we do the simulations into that? Probably that we said let's call it as a level 4, and then if we have a further advancement, more autonomous ways, more broader, inclusion of assets and infrastructures, probably level 5. And then what's the benefit of it? Because we said maybe this business benefits are just at design level or manufacturing level, maybe a component level or prototyping level. But then this is maybe for a service level or maybe monitoring assets, tracking assets, asset health, condition monitoring, all that benefits will come. But then the level 4 will bring more like predictive maintenance, prescriptive maintenance, design, data driven product designs or closed loop product lifecycle management, real time optimization, all that business benefits will come. And then level 5 will bring more, a lot of benefits to the. That's why we said if you want to call, instead of just calling a digital twin, can we then link it to the levels, maturities, right? And then that was the aim. We wanted to building blocks which will also enable the building blocks, features and outcomes. And then digital twin, and then it can be easier to deploy. Let's start from level 1 to 3, right, rather than just jumping into the level 5 stepwise approach. And then it also helps manufacturers in different ways, and taxonomy can help to alleviate the confusion around the term use, a digital twin. And the level 5 digital holy grail, or the holistic view of a digital twin representation, which can bring the multiple aspects, or it is a more broader digital twin or more better the digital twin. So for example, when I was working in Infosys, we built digital models of the human heart, right? Now that with, and then simulation of the human heart, without really having this physical layer. So maybe it was a level 1 or 2. If I want to call a digital twin, I can call either virtual twin or a level 1, 2 of the digital twin. If probably if I now have something, say sensors connected, simulation connected, all that, probably level 3 digital twin or simulation data driven digital twin, and maybe those kind of things. And other cases are level 4 or 5, I already demonstrated, so I just wanted to bring some clarification. Now, if someone want to build the digital twin, how they can go on building the digital twin? Maybe I'll quickly jump because I know I'm short of time, but uh, I'll just do a very quick run. So my first step is you have to imagine what you want to do, achieve, identify various assets, sensors, the same thing if I talked in that smart pod digital twin, right? Then pilot, create a small pilot, industrialize, then start deploying at a larger scale, and then you get the lot of information, and that's what is a level 1, 2, 3, 4, 5 kind of digital twins you can build. You can get a lot of benefits. Possible applications are across the products, services, production lines, everywhere you can do that. There is a huge opportunity. Maybe I wanted to talk something more on building the digital twin, but use how you can get started using the digital twin or industrial IoT using Raspberry Pi. But probably in the interest of time, maybe I'll just directly jump to the, if anyone interested future, let me know. But I'll just jump to the conclusion because I just don't want to disturb the schedule. So IoT definitely is disrupting. IoT is one of the technologies. Industry 4.0 is further disrupting not just automotive but all manufacturing. Digital twin is one of the latest trend in Industry 4.0. There are several challenges. And in the academic setup or anyone in the industrial setup can get started with a simple as a Raspberry Pi, which can enable you to bring a lot of technologies very easily to build the digital twin. With that thought, probably I'll make stop now, and maybe I'll give you few minutes to ask any questions if you have, but you can take my contact from Dr. Piyush, or you might have noted my emails and contact on the slides. If you have any questions, feel free to ask.
Thank you, Dr. Parle. Now, I request to the participant if there is any question, then please write in the chat box or you can raise your hand. I think people has found some
Yeah,
difficult.
yeah, someone has raised their hand.
Yes, one participant is there.
Yeah.
Let me unmute him. Yes, Wagela sir, you can ask.
I
Hello.
think he's not still mute. He's still muted. I think he has to unmute. So Agila sir, probably you have to unmute yourself.
His mic I have already unmute.
Okay.
I allow him to speak. Or you can write in chat box.
Yeah, no problem.
I have already unmute him.
Allowed, but he need to unmute. I think he has not
Yeah.
unmuted. If he is speaking, he need to unmute.
Are you here, Wagela sir? I think we are not getting the response in any form from
Yeah,
inside.
yeah, no problem. Okay, so thanks a lot,
Okay.
everyone, and thank you, Piyush sir. It was nice
Thank
talking
you.
to you, seeing you, and I hope that's some useful thoughts there
Yeah.
to people to take. Thank you very much.
Nice to see you. Okay. Thank you very much.
Bye-bye.
Okay, bye-bye.
Bye.